Hello, this is Team 2. Today, we are going to introduce our adjustable luggage bag with a Miura pattern. These days, many people feel unsure about which luggage to choose due to the wide range of options available. For this reason, they often run out of space while packing and need to switch to a different bag. In addition, people have likely struggled with luggage that is too large to fit in the storage compartment, as shown in the video. Furthermore, at airports, baggage regulations and size limits often lead to people kicking their bags or removing the wheels to meet carry-on requirements. In summary, choosing the right size for conventional luggage can be challenging due to the variety of options and the changing volume before and after a trip. Additionally, finding storage space can be tough as zipping and folding methods don't effectively reduce luggage volume. Finally, if a luggage bag doesn't meet airline regulations, it may lead to extra costs and delays. To overcome these limitations, efforts have been made to design luggage with adjustable sizes, commonly using zippers. However, the adjustable volume is fixed and discontinuous, and finer adjustments require many zippers, making the process inconvenient. Another approach is a box-shaped folding luggage bag, which allows adjustable sizing by folding its sides. However, it's difficult to make continuous adjustments, and storing items becomes challenging once folded. To make a continuously expandable luggage bag, we encountered some problems to solve. First, we needed to make a folding pattern that could be stretched or folded with a single do-F, and we chose a Miura pattern. Second, we needed continuously expandable frames to hold the origami pattern, and we made a telescopic boom frame with PVC pipes. Finally, we required a locking mechanism to hold the origami or frame from shrinking due to gravity. We used extra luggage bag handles as locking linear guides. To construct our pattern, we considered several constraints. First, it must be expanded while maintaining its flatness. The water bomb pattern can't maintain its flatness since it has positive Gaussian curvature. The Ronresh pattern was too auxetic. Therefore, we chose the Miura pattern that maintains its flatness and is less auxetic in some range of folding angles. In addition, we wanted the pattern to be rigid enough. Both Ronresh and Waterbomb have a high degree of freedom, which makes them flexible and weak to external forces. On the other hand, the Miura pattern is rigid enough since it has only one DOF. Miura pattern can be determined with three parameters, which are the width and height of the facet and the angle of the facet. We used 30 mm as both the width and height of the facet and 45 degrees as the facet's angle. We chose the facet width and height not to make the pattern too thick, and we chose 45 degrees as the facet angle by comparing various face angles. With a small facet angle, our origami can't maintain its rigidity due to face deformation. With a large facet angle, our origami was too auxetic that it tried to extrude the predefined width, which led to an insufficient operating range. Our prototype is here. Miura pattern printed paper sheets became the sides of suitcase. We simply applied cart and suitcase handles to implement the suitcase structure with resizing mechanism. PVC pipes with different diameters utilized to implement the telescopic boom of adjustable column. You can find our implementation of adjust mechanism in those videos. If the users want to resize their suitcase for their own reasons, this adjustable mechanism makes it possible. For checking the strength of the Miura pattern, we executed the test. As you can see in the video, when the total weight became the 7.2 kilograms, Miura pattern deformed drastically. We found that this ring-based interface and plastic paper material were the main reason of large deformation. When we fixed the rings with tape, deflection was improved. So, those issues can be largely improved by the harder materials with solid interface between pipe and pattern sheet. We prepared an overview of the areas and potential directions for improvement of our current prototype. First one is about the structural strength. Because we used the plastic sheets to construct the large foldable wall within limited time frame, we believe using more rigid material like metal sheets and hinge structure would improve the strength of the foldable wall itself. In addition, in the interface part, the foldable wall and the telescopic boom are connected using rings that have excessive play. Therefore, adding wall support structures or linear guide would help eliminate the structural weakness caused by the ring interface. Second point is about the design completeness. First, the connecting rings protruded externally due to the use of rings and telescopic booms. We believe the pre-mentioned linear guide would be helpful, because its connections can be positioned internally. Second, because the walls are foldable, items in the carrier may get stuck between the faces. Therefore, the stretchable rollers, like those used in vehicle sunshades, can be used to cover each side of the foldable walls. It will prevent items inside the carrier from getting stuck by the folded walls.